Welcome to lesson number 7 on active probes. Thus far during this video series on oscilloscopes, we've only used passive probes for our measurements like this one. Passive probes are the most general purpose type of probe, and as I mentioned in lesson number 3, it may be the only type of probe you'll use during your engineering studies. But passive probes do have some limitations, and I want to introduce you to some probes that you'll probably need in the future, maybe even during some of your upper level circuits classes. Hi, I'm Johnny Hancock, Product Manager for Keysight Technologies Infinivision Oscilloscopes. Let's start with a review of the limitations of passive probes. Passive probes have limited bandwidth. About 700 megahertz is the tops you're going to get out of the standard passive probe. Passive probes can only measure voltage. They can't directly measure current. Passive probes can only make measurements relative to ground. They can't directly measure differential voltages. And the standard 10-to-1 passive probes have limited voltage range. They can't measure thousands of volts. You'd blow one of these things up if you connected it to very high voltage. Let's now look at some of our alternatives for these cases. This is a high-frequency active probe. It has a bandwidth of 6 gigahertz. Now, it wouldn't make a whole lot of sense to connect this 6 gigahertz probe to the scope that I've been using for most of the demonstrations because it only has a bandwidth of 200 megahertz. Whatever the weakest link is what the system bandwidth is going to be. So I have another scope over here that has 6 gigahertz bandwidth. That mates very well with the 6 gigahertz probe. Now we call it an active probe, as I mentioned when we talked about passive probes, because this probe has active circuitry in it. It has a differential amplifier very close to the tip up here. And what that means is that it requires power. These pins on this end of it feed power and control signals to this amplifier. It picks up power from pads on the oscilloscope as well as the control signals. Now, some other things to point out about this. This probe is not nearly as usable as a standard passive probe. The only way you can get really high bandwidth out of a probe is to keep all the connections, the wires at the end of it, very, very short, because just a little bit of wire length can add a lot of inductance and reduce the total bandwidth. So making high frequency measurements is it's not exactly a walk in the park. Now, oscilloscope vendors typically provide some accessories for you to help you with the usability. Here's a couple of them I have here. This is a tip that I can replace, and you probably can't see it, 2 very short tips. Very difficult to probe. You can replace it with this tip that has a couple of short wires coming out that you can solder on to the board. Then you can take your hands off. And this one here has sockets, so you can plug it into a header connector. And that's what I'm going to use in just a minute. And so I'm going to demonstrate something to you. What we're going to test is signals coming out of my USB drive. We have a special fixture we made here. This is my probe tip that's got the socketed connection. It's connected to a couple of header connectors. And we're going to look at the signals going in and out between my USB drive and the oscilloscope, and we'll see how fast they are. So let's first of all plug in the probe, and then we'll connect the probe to the DUT. So this is a USB 2.0 serial bus signal. It runs at 480 megabits per second, but the frequency content can be a lot higher, up to about 2.5 gigahertz. So my 6 gigahertz probe, my 6 gigahertz scope is more than enough bandwidth for this signal. Now this signal is differential. You probably see a graphic on your screen right now that illustrates when one side of the bus goes high, the other side of the bus goes low. But what if a transient or noise couples on to the differential bus? Well, if it's common mode, the same transient is going to be in phase, coupling on to both the high side and the low side, and the net result, the differential, it subtracts out. That's the real benefit of a differential bus, is that it has much higher noise immunity than what we call a single-ended bus, a bus that has a signal line relative to ground. Let's take a look at some of these signals right here. I'm going to turn on the zoom time base of this scope, and I'm looking at the sync pulse area of this packet of data. And this is the sync pulse, it's repeating clocks. It's actually only 240 megahertz. But how much frequency content is in a 240 megahertz clock? Well, we haven't got to the FFT lesson yet. It's coming up, but I'm giving you a little sneak preview on that. So I'm going to turn on FFT, and these peaks here represent different frequency components. And this one here is the fundamental frequency, which is 240 megahertz. That's the toggle frequency. And then you have the third harmonic, fifth harmonic, and there I can see a seventh harmonic. That seventh harmonic is almost 2 gigahertz. So this really stresses the importance of using a high frequency active probe and a high frequency scope on something that you may not think, 480 megabits per second, why would I need 2 gigahertz bandwidth? You do because of the higher frequency content in digital signals. This is a high voltage differential active probe. So it also has an amplifier in it, and it requires power. This particular probe gets power from a battery that's installed inside here. So it doesn't pick up power like the high frequency probe over here. Now, this one has a 10-to-1 setting and a 100-to-1 setting, so we can measure very high voltages. Now, notice this one does have very long leads, very different than the high frequency probe. This probe only has 25 megahertz bandwidth. And so the inductance of these leads is relatively small compared to the bandwidth. But for high voltage measurements, typically you're connecting to pretty big terminals, big wires, and so you need long wires and big connections like this. We'll make a measurement in just a minute. This is a current probe. It can measure current. The way it measures current is you'll have to create a loop, typically from a wire, or maybe the way you lay out your PC board, and then you clamp around the wire loop. And there's what's called a Hall effect sensor near the tip of this probe that, if you remember from your magnetics classes, the right-hand rule, the magnetic field around a wire, if current is flowing and current flows in the direction of the thumb, I think it's right hand, not left hand, pretty sure it's right-hand rule. And that sensor converts, it picks up that magnetic field, converts it to voltage, and then the output of the probe's just a BNC, and we plug it into our scope. It delivers voltage to the scope. And now the scope measures voltage, but then we can convert it back in terms of the way we make the measurements. So, and also this one is battery operated. Let's go ahead and turn it on. And let's also connect up our high voltage probe and turn this one on. And what we're going to measure is the input AC voltage to this function generator. Has nothing to do with what the generator is generating. Just think of this as any system or any DUT. And we're going to measure the input voltage and the input current. And ultimately, in the lesson after this, we're going to measure the power consumption of this particular instrument here. So I have my high voltage differential probe connected to the AC input of this generator, as well as the current probe connected. Now, I'm not going to show you how I connected it because I probably violated some safety standards, but you can probably guess. So the first step is we need to tell the scope what the probe attenuation factor is or the conversion factor of each of the probes. So I'm going to go into the Channel 1 menu, select probe, and you can see it says 10:1. That's where it was set the last time. I've got my high voltage differential probe set in 100:1, so I need to change that to 100:1 so all the measurements will reflect that level of attenuation. Then just set it up like you would, we've discussed earlier. This is the AC input in this room. It is really ugly. Look at all that interference or garbage riding on that sine wave. I've seen it in this building before. I did this test at home yesterday. I had a pretty clean sine wave in my home lab. But this factory, there's lots and lots of equipment connected to the grid, and it can cause interference on the grid, and I think that's what we're seeing here. It's something called current harmonics. There's a specification for it. Let's make some measurements on this AC voltage input. So I'll select measure. The two default measurements pop up. It says 60 hertz. That's what the frequency is here in the US. In Europe, it'd probably say 50 hertz, similar in Asia. The peak-to-peak voltage, it says 340 volts. Now you're thinking, in the US, don't they have 115, 120? That's RMS. So let's select an RMS measurement, and it measures about 120 volts, pretty much what we would expect. Let's look at the current waveform. I'm going to rescale this first, move it up here, so we can separate the two. Turn on the current. Now I have to do the same thing. Go into the probe menu, and I had previously selected, normally it comes up in volts. If I select amps, now it knows it's measuring current. So it's going to convert voltage to current. And then there's, instead of a probe attenuation factor, it has a conversion factor. In this case, I'm going to use the default 0.1 volts per amp. That's the conversion factor. That's pretty much equivalent to a 10:1 attenuation. Next, let's just rescale the current. And you can see it's not a sine wave. It's pulsed. That's pretty representative of a piece of equipment that has a full wave rectifier in its power supply. It full wave rectifies it, then it charges the capacitor, filters it, and then as the voltage drains down, then it will turn it back on and start pulling more current. And so it's pulling it in pulses. Let's make some measurements on that. And by the way, I'm not driving anything with this generator, and so it's not pulling a lot of current. Let's do a peak-to-peak measurement on this current. So peak-to-peak is, oh, I selected peak-to-peak voltage again. Let's do peak-to-peak current. It's almost 4 amps peak-to-peak, so it's approximately plus 4 amps peak minus, or 2 amps peak minus 2 amps peak. Let's do the RMS. About 350 milliamps RMS. Oscilloscopes are often just half the measurement solution. The other half is selecting the right probe for the job, as we just demonstrated using 3 different active probes to measure a high frequency differential signal, a high voltage AC signal, and AC current. You may be wondering about power now, since power is the product of voltage and current, as you may have already learned in some of your circuits classes. That's what we are going to be talking about and demonstrating in our next lesson, which will be on oscilloscope waveform math functions. See you in lesson number 8. Go Purdue Boilermakers!